Have you ever wondered what makes a computer work? Our daily lives are intertwined with these wonder machines that can take in data in the world, process it, and tells us all sorts of information. They can help navigate self-driving cars through the streets, project the trajectories of clouds and storms, or help some rich influencers tweets. Or is it X's? Well, whatever is the case, these silicone boxes have shaped human history. It is really interesting how these are made. The people behind it place so much thought on the mechanisms on both the hardware and the software. These range from the computer architecture that looks like miniature cities, to the compiler that converts our human readable instructions to incomprehensible machine code. And because of the interesting mystery just hidden around our screens, I spent my entire past summer just so I can make my own homebrew computer. Before showing you my creation, I have to fill you in on what a computer is to make sure that we are on the right track. In the ancient past, the term computer was actually a job that people can take with the help of the latest technology around, the abacus, or whatever this thing was that Hephaestus made for the Greeks. As history marches on, human computers and their analog counterparts compute a wide variety of data, from calculating the return date of Halley's Comet to figuring out how currents and winds move ships amidst a stormy sea, and to peppering enemy aircrafts in the sky. Computers were essential during the World Wars as those who can gather, transmit, or track information about an enemy and strategize on it determines who get to be the winner of a battle. The arms race of wars on manipulating information have made analog computers and their digital cousins advance in intricacy, and so did the progress of the maths and science behind it. And between the world wars, one kind gay bloke, the child himself, Alan Turing, formalized the idea of a computer. It was to find an answer to a fundamental question of whether math is undecidable. He was searching if there's a statement in mathematics that doesn't know whether it is true or false. Could there be a problem, proven to be impossible by math itself, to lead to the correct answer to a simple yes or no question? Well, yeah. Apparently, there exists a problem that can be picky on which answer it wants. But before he came to that conclusion, Alan Turing had to answer the question on how do you prove or compute a statement? It has to be something that operates with clear and definite rules. So, he came up with the Turing machine. Here's a simplified definition of what a Turing machine does. You can write information on a very long piece of tape, such as ones and zeros. X ahead, that can read the info, change the next location, and rewrite the data on that new place. Based on the new info on the really long tape, the head executes the corresponding instructions that dictates on what to do next. And finally, it can stop executing if it receives the instruction for it. The wonderful thing about the Turing machine is that it can consistently solve tons of problems that are computable. The computer that I made, the E-2, can also do the same as a Turing machine according to its own instruction set, so it can be called Turing complete. You might be wondering why is it called the E-2? Well, there has been some history behind it. If you look over here in my folder, there has been multiple versions in the past that really frustrated me and have to restart over and over again. If we open one of these files, for example, the C-9, open this one with the original programming, you can see already the complexity this circuit has. And because of this incomprehensible complexity, I have to restart again and again, building my understanding of how each component works in a computer. I was able to overcome this problem thanks to the power of simple organization. You can see the data of each component has and some labels that I can attach to each component using the tunnels here. Thanks to that, I was able to compress all of the workload much more neatly and understand it much more comprehensively. Well, what can a computer like this do? Well, there's some things I want to showcase. First off, I can program almost anything on this computer with this assembly-based instruction set right over here. Then, with the help of this Python-based compiler over here, I can program almost any instruction that is based on this instruction set and turn it into machine code that the E-2 uses. For example, this one. I can copy and paste it to the right section of the data. For example, this one. No. There we go. This one, you have the data. And for this one, just copy this. It goes into this one. Now, if we press play, we should be able to see it right here. You can see this computer taking in the code that I developed and outputting it to this console. If we slow it down to like 1 Hertz right over here, you can see the computer is taking in the instructions here, as you can see here, incrementing, taking the data here, and interpreting it using this control unit, which is the head of this Turing machine. And based on the instructions, outputting it here to this console. In this case, outputting the word stop with an exclamation point. Another program we can do is a multiplication program, which multiplies 2 numbers together and outputs it to the console here. Now, I already prepared the program in here. Yeah, I already copy and pasted it here. Now, let's try inputting 2 numbers here. 2 and 4. Now, if you press play, it should give us the number 8. There we go. Now, let's think of 2 numbers again. How about 5 and 6? If we look here, it should give us number 1E in hexadecimal. This is because the algorithm uses hexadecimal for its input and its output. Normally, it should be 30 in base 10, but again, this is in base 16. If we go for higher numbers, for example, let's take for a random number. 113 and 2. Now, it'll take a while to calculate this number, this equation, but it should give us the same number in decimal, which is 226. This demonstrates that it can function similarly to a calculator. But friends, it's more than a simple calculator. There's a bit of fun in this computer, for it doubled a bit more than just calculations. Friends, it can also display some graphics. There we go. Yeah, this is in real time over here. You can see that the screen is playing Bad Apple here. It's a bit slower than usual when you compare to the real video, but it's the best that the simulator that I'm working on, Logisim Evolution, can display. Let's play a bit more of the video. Hopefully you see the editing there. But the graphics on this computer ain't just black and white. No, if you look to the screen on the left, this yellow screen, you can see that it actually can display... Oh wait, hold on. If you look at the screen on the left, this yellow screen, you can see that it can also display in colors. Yeah, it's a bit slower than the screen on the right here. It actually updates per pixel, unlike the right one which updates per line. It could display faster if you remove the CPU that's handling the lyrics on this console right here. And if we go to the next scene here, here's the video without the CPU and the lyrics. There we go. You can see the video is being displayed with just the screen handler here and the memory for it. You can even see the frame rate here being much faster than the previous simulation. The reason why it displays much faster is because it doesn't have to simulate so much components, so many of them, such as those inside the E-2. You can even see the characters here in the opening of Oshinoko. It's quite a marvel if you think about how many frames are being updated here per second. With the help of editing, we can also compare the results here. The videos that you see here on the screen are converted using a Python program that converts the original video into individual PNG frames. This is then downscaled and then written into machine code that the E2 computer can display. Since it can play these types of graphics, it must mean it can display these. With a slight modification on the settings of the video converter, I can transform some popular names with the quality of the early internet. And since this is made from logic gates, this homemade computer could be theoretically be built in the real world with real logic gates and other IC chips which can also display them as well. Which is amazing to me. There are already great examples such as Ben Eater's computer, which is how I got interested in designing my own one. Although, if I were to build a real one, I would need a lot of saving, some hard work, and some study of basic computer engineering. But at least the designing part is already done. It already took a lot of hard work and thinking into designing one. And the video graphics part was immediately a huge pain to learn at first. Even so, it was worth learning how computers and basic graphics work. Not to mention, I really had fun learning and designing it. Although I want to optimize this design to make it more efficient, college is coming up soon, so I might have to do it next time when there's tons of free time around. And so I have to wrap up this project and this video about it. I just want to share with you guys what I experienced these past few months on this sort of informative, sort of blog, sort of freestyle video. Computers are very useful for humanity, and we should appreciate how much thought the designers must have put as we use it for our daily lives. And that's what I want to share with you all. And with that, I bid farewell. Bye bye.